All right, hello. Um, I am going to help you through the B Honors lesson for 6.2e. So we're going to work on creating cubes and nth roots, and it's kind of a long lesson. So I'll do all the examples, even though in class we'd probably skip some of the examples, or I'd have you try some on your own. So we're going to work on creating cubes and nth roots. So the first question is find the volume of the cube and describe the method you're using. So here's a cube, actually a Rubik's Cube, right? Well, this cube, since all of the dimensions are equal, this is called a perfect cube. See, all of the sides are exactly the same. So the width is 3 units. The length is 3 units. Maybe you'd say the height. Oh, I should probably spell that right. Height is 3 units. So to find the volume, you just multiply 3 times 3 times 3, or 3 cubed, and we get 27 units cubed, or cubic units. So we're going to just fill out this table here. Here on this side, we're going to put, and it says for perfect cubes, so you can assume that they'd look just like this. So if the side length is in this column, the dimensions in this column, the volume in this column using exponents, and the volume of the cube with units. So, like writing out cubic units. So if the side length of a cube is 2, then the dimensions are 2 by 2 by 2, and the volume would be 2 cubed. So we'd say it's 8 cubic units. Okay, over here we have dimensions that are 5 by 5 by 5. So that must mean that each side length is 5 units. So we have 5 cubed and 5 cubic units. Okay, here they're actually giving you the volume. So kind of moving backwards, you know that 8 to the third power really means 8 times 8 times 8. So you have each side must be 8 units. And so you have 8 cubic units. And then here, this is just side, like generalizing this whole pattern. So if you have a perfect cube and you know the length of the side, then you know that it's side times side times side, which is side cubed, which is whatever that side is, cubed. And you can write units cubed instead of cubic units. So if given the side length of a cube as x, what formula represents its volume? So like if this was x instead of s, it would be volume equals x cubed, right? So if given the volume of a cube as v, so if they gave you the volume and you had to find the side length, you're kind of working backwards, and you want the cube root of whatever v is. Whatever the volume is, that's going to be your side length. So cube and cube root are inverse operations, just like addition and subtraction, multiplication and division, squaring something, taking the square root. So true or false? Square root of 9 is the same thing as cube root of 27. Well, what is the square root of 9? 3, right? Because 3 times 3 is 9. Because this index here is 2. And what can you multiply by itself 3 times to get to 27? 3. So this is true, right? Those are equal. So 3 times 3 is 9. And 3 times 3 times 3 is 27. Okay, so we're going to go ahead and simplify the cube roots. Now you need to make sure that you take out groups of 3. So just like when we did square roots and we would take out perfect squares, what we're going to look for is perfect cubes. So you can still use the same method that I was showing you before, where you start with the radicand, the number inside, and you start dividing by prime numbers. So if you don't know the perfect cube that's inside of 64, then you just start dividing by 2. So 64 divided by 2, 32. 32 divided by 2, 16. 16 divided by 2, 8. 8 divided by 2, 4. 4 divided by 2. Okay, so now instead of looking for pairs to take out, you're actually looking for groups of 3 because it's a cube root. So I'm have 2 times 2 times 2, a group of 2's, another group of 2's. So I know that both of those, I have a 2 on the outside times another 2 on the outside. So I know that I'm left with 4, and I don't have anything left on the inside. So that just tells me that 64 is a perfect cube because 4 times 4 times 4 is 64. All right, let's work on this one. Now, just like we split up square roots, we can do that with cube roots too. So I'm just going to split this up, and I'm going to make it cube root of 27 over cube root of 125. All right, well, we already did the cube root of 27 up here, so we already know that the top is 3. And then 125. So think about 125. 125 divided by 5 is 25, and then divide by 5 again, you're back to 5. So this is 3 over 5. So each of these is actually a perfect cube. 27 is a perfect cube. 125 is a perfect cube. So you'll start recognizing those after a while. Okay, cube root of a decimal. Well, you could do this a couple ways. One way you could do it is you could change this if you don't like decimals. You could change this into cube root of 27 over cube root of, this is 27 thousandths, right? So you could change it to this and then simplify each one. So 27, we already know is a perfect cube, 3 over, well, 1,000 has 3 zeros in it, so that's a perfect cube, 10. So you could answer it as 3/10, or you could do it with a decimal. So you could say, all right, well, I know that 27 is 3 times 3 times 3, but it has 3 decimal places. So that means that each of my 3's need a decimal place. So I could answer it as 0.3. So far, all we've done is worked on perfect cubes. So notice that we don't have any radicals left in our answer. All right, 32. Well, 32, I can divide it by 2, 16. I can divide that by 2, 8. I can divide that by 2, 4. I can divide that by 2. And remember, I'm looking for groups of 3. So by now, from this problem and this problem, you should recognize that 8 is the perfect cube because it's always 2 times 2 times 2. But I have this group of 2's left over. So I have one group of 2's that comes outside, and then I just have this leftover group of 2's. So I have 2 cube root of, and whatever's left inside, you multiply. So 2 cube root of 4. And you have to make sure that you put that index in there, and don't forget, because if you didn't write the 3 in here, cube root, then if you just leave it off, it means that it's a square root, and you know that there's a square root of 4. So you got to make sure that you put the index in there if you're left with a radical. All right, let's try 108. So 108, you can start dividing by 2, 54, divide by 2, 27. Okay, 2 doesn't go into 27, so I'll try 3. So 3, 9, 3, and 3. Okay, I have a group of 3's here. So I'm going to take that outside. And then what do I have left in? 4. So I have 3 cube root of 4. And it kind of looks strange having a 4 left in there because we're used to having square roots and it coming out, but There's no cube roots inside of 4. All right, let's try this one. 128x to the 6, the cube root. So I have 128 divided by 2, 64. Oh, 64. Remember back here, we did cube root of 64. We already know 64 is a perfect cube. So I already know that this 64 is a perfect cube, which is 4. So the 4 is going to go on the outside. And when I look at this x to the 6th, I need to know how many groups of 3 x's can come out. So since I have x to the 6th, I actually can take 2 of those groups of 3 out. And then what's left inside? Well, I have cube root of, and then what's left inside? Just the 2. The 2 is left over. All right. So find the length, the side length of this cube. Well, we already know that volume, so they gave us the volume. Volume is x cubed, right? So if they gave me the volume, I'm going to have to do the inverse operation of finding the cube root of this volume. So I need to figure out what's the simplest radical form to write the cube root of 1029. So I could go out here and start with my little factor tree division here. So 2 doesn't go into this number, but 3 does. I know 3 does because 1 plus 2 is 3 plus 9. And then 3 goes into 1029 343 times. Well, 3 doesn't go into this, but 7 does, 49 times. And then I have 7 times 7. All right, remember I'm looking for a cube root. So I have a group of 3 7s. So that goes on the outside. And then, don't forget your index. What's left on the inside is 3. And then I would just want to put meters, right? Because that's what the unit is. So that's the side length. So does the cube root of 8 plus 64 equal 2 plus 4? Because 8 is a perfect cube, which is 2, and 64 is a perfect cube, which we already discovered was 4. So it seems like maybe this is true, but actually you would have to sort of think about order of operations. I'm going to go ahead and add these inside here. So this is actually the cube root of 72. And I want to know, does this equal 6? Well, a couple of reasons why not. 6 times 6 times 6 doesn't equal 72. It equals 216. Or you could actually go ahead and find what is the cube root of 72. 72 divisible by 2, 36. Divisible by 2, 18. Divisible by 2, 9. Divisible by 3. So actually, the cube root of 72 is actually, here's a group of 2's, 2 cube root of 3. So that's not the same as 2 plus 4. So that should just tell you that you can't split up addition inside of a radical like they did here. So examine the cube roots of a negative value to complete the following. So does the cube root of negative 8 equal the square root of negative 8, right? Because this is just square root. Explain why or why not. Well, they cannot be equal because they have different indexes. So, and cube root of negative 8 is negative 2 times negative 2 times negative 2, right? You can have negative 2 times negative 2 is positive, and then another negative. So that works out. But there's no numbers that you can multiply by themselves twice to get to negative 8. So square root of negative 8 is not a real number. Okay, so if I look at, can I simplify a negative cube root? Well, up here it looks like I can. So I'm going to go ahead and take 216 and figure out what the cube root of it is. So 216 is divisible by 2, 108, divisible by 2, 54, divisible by 2, 27, divisible by 3, 9, divisible by 3. Okay, so I have a group of 3's and a group of 2's. So I take out a 2 and I take out a 3 because I have 3 3's. And I have nothing left inside, right, because I have these two groups. So I have 6, but 6 times 6 times 6 is not negative 216. So what I actually need to do is make this negative 6. And that would be the cube root of negative 216. So now you know that 216 is also a perfect cube because when you simplify it, you end up with nothing else in the radical. So explain in words what happens when taking the cube root of a negative integer. Well, the cube root is negative because a factor, a number that you multiply by itself, a factor multiplied by itself 3 times results in a negative number. And you can see that no matter what number it is. So if you have a negative times a negative times a negative, it's going to be negative because you have a pair of pair of negatives that make a positive, and then you always have this one negative left over. So now let's examine the fourth root of a value instead of square root or third root. I'm tired of green, so we'll switch to blue. Okay, so does the cube root of 16 equal the fourth root of 16? Well, this means that I need a number that I can multiply by itself 3 times, number times the number times the number, to get to 16. This means that I need to multiply a number by itself 4 times to get to 16. Those are two different things. So there's no number that I can multiply by itself 3 times and get to 16. I mean, I can figure out the cube root, like simplify the cube root of 16, but it's not going to be just one single number. But what number can you multiply by itself 4 times to get to 16? Well, 2 times 2 times 2 times 2. So the fourth root of 16 is actually 2, but the cube root of 16 is, well, 16 divisible by 2 is 8, divisible by 2 is 4, divisible by 2. So actually I have a group of 2's that comes outside, but then I still have this 2 left inside. So those are not the same thing. Explain in words how simplifying a whole number with a fourth root is different than simplifying a cube root. Well, I kind of showed that up there, right? So I think that's shown in previous problem. Basically, a cube root, you take out groups of 3, and a fourth root, you take out groups of 4. So explain why the fourth root of negative 81 has no solution. Well, why does it have no solution? Because it's an even index. An even index will not have a real answer if the radicand, the number underneath the radical, is negative. So think about that. If I had a negative number and I multiplied it, so I have a negative number, like let's say negative 2. Negative 2, oh, actually, let's use 3 because that seems like what it would be. So negative 3 times negative 3 times negative 3 times negative 3. Well, that's going to be negative 3 times negative 3, positive. Negative 3 times negative 3, positive. That's going to be positive 81. There's no way that I can have four numbers, negative numbers, multiply by themselves and get to a negative number. Okay, so in this module, you have seen square roots, cubic roots, fourth roots, but it is important to note that roots come in all sizes. So if n is a positive integer, meaning the index is a positive integer, and a is a real number, any real number whose nth power equals a is called an nth root of a, denoted as an nth root of a, where n is the index. So simplify the following nth roots. Assume all variables represent positive numbers. So what they're saying here is, I'm going to just plug in numbers in this nth root. Maybe it's a fifth root, maybe it's a sixth root, maybe it's a cube root, maybe it's a fourth root. But whatever the nth root is, that's the size of the group that you're going to take out. So if I look at this index, 5, this just tells me that I need to take out groups of 5. Okay, so I'm going to go ahead and take 96 and go ahead and do my little division prime number tree thing here. So 96 divided by 2, 48, divided by 2, 24, divided by 2, 12, divided by 2, 6, divided by 2, 3. Okay, so now I'm just looking for groups of 5 here. So I see here I have a group of 5 2s. That's going to go on the outside, 2, because I have a perfect group of 5 there. And then I have this 3 left over, so that's going to go on the inside, but I need to remember that I was dealing with a fifth root, so I need to make sure I put the index in there. Don't forget the index. Don't forget the index. We were doing square roots for so long, it seems like it's hard to remember to put the index in there. Okay, so now, since this index is 6, I want groups of 6. I'm looking for groups of 6 when I do this prime number tree. So 192 divisible by 2 is what, 81? Or no, 91? Wow. 192 divided by 2. I shouldn't be doing this at night. Okay, 96. That makes sense. Okay, divisible by 2 is 48. Divisible by 2 is 24. Divisible by 2 is 12. Divisible by 2, 6. Divisible by 2, 3. Okay, so now I see I have actually a group of 6 2s here. So that's going to go on the outside. And then what I have left over on the inside is this 3. And then I just need to remember to put the 6 here as the index. And make sure that you put it in that little crook of the radical so it doesn't look like it's a power on whatever's on the outside. Okay, here I'm looking for groups of 4. Well, think about how many groups of 4a's is in a to the 5th. I mean, you could write it out if you wanted to think about it. I mean, what's a to the 5th? It's really a times a times a times a times a. And then you could pull out, one group of 4. But you should be able to think of, okay, I know that there's 5 A's. I can take 4 of them out. So I have an A on the outside, and then I have 1 left on the inside. So this would be A on the outside, A on the inside, and then I have 4th root. Okay, here I'm looking for groups of 6. So I shouldn't have to go back here and do this, like write out 8 x's and 10 y's, I should just think, okay, how many groups of 6 x's can I take out of 8 x's? Well, I can take out 1. So I have an x on the outside. And then what am I going to have on the inside? I took out 6. I still have 2 left. And then how many groups of 6 can I take out of 10 y's? 1. And how many do I have left? I still have 4 left. And then I need to remember to put my index right here, 6 through, because I was looking for groups of 6. So complete the table below and state the value of the nth root of a given specific requirements for a and n. Provide an example to support your reasoning. So we're going to this chart is to help you sort of generalize, sort of summarize when is something a positive value, a negative value, what's my result's going to be. Okay, so n, for this box, n is an even value, like maybe n is 2 or 4 or 6, something like that. And a is a positive number. Okay, so what's my result going to be? Well, let's just go ahead and make an example. Like, let's say my index is 4 and a is 16, a positive value. Well, this is 2. So I'm going to get, in any situation where my index is even and my radicand is positive, I'm going to get a positive solution. Okay, but what if n is an odd value? So what if n was 3 or 5 or 7, something like that? So they actually put the answer in here, positive solution. But if you had a cube root of, let's say, 8, so remember a is positive and n is odd. Well, this is 2, so I'm still going to get a positive solution. Okay, what about, though, if a is a negative number and my n is an even number? So in this case, n is still 2 or 4 or 6, some even number, but a is negative. So let's just do an example of that down here. Let's say, okay, my n is an even value, so like 4, but my a is negative number, negative 16. So is there any number like 2? Can I do negative 2 times negative 2 times negative 2 times negative 2? No, that's going to end up being positive. So whenever you have an even index and negative radicand, that's no solution. No solution, no real number. No real number. Because you can't multiply a negative number times itself an even number of times and get a negative number. Okay, but what about if n is odd, like 3 or 5 or 7, and a is negative? So let's do an example of that. So my index is 3, that's an odd number. My radicand is negative 8. Well, this is negative 2 times negative 2 times negative 2, right? So my cube root is negative 2. So in that case, I'm going to get a negative solution. Okay, so thinking about this chart, this can kind of give us some shortcuts on our next page, which is a bunch of examples. All right, now think about, don't waste your time doing problems that are going to have no solution, right? Okay, so sort of checking with my chart here, right? Well, here I have an even index with a positive A. So an even index with a positive A. I know I'm going to get a positive solution. So I'm going to go ahead and work on this. I want groups of 4. So I'll start with 81. 2 doesn't go into it, but 3 does. 27, 3. Okay, I have a group of 4 3s. So that must be a perfect 4th root. 81 is a perfect 4th root because I ended up with nothing left over. Okay, now here I have 7 as my index, which is odd, and I have a negative value in as my A. So I know that I'm going to get a negative solution. So what number can you multiply by itself 7 times and get -1? Well, -1. Okay, here I have a positive number and an even index. So I'm going to look for groups of 4. So I have 144, I can divide by 2, get 72, divide by 2, 36, divide by 2, get 18, divide by 2, 9. Well, then I have to divide by 3. Okay, here I have a group of 4 2s. They're going to go on the outside, 2. And then I have to, since I have something left on the inside, I have to put this radical and put my 4 there. And what do I have left on the inside? I have 3 times 3, so that's 9. Okay, here I have a negative value, and I'm looking for the 5th root. Well, this is odd, and this is negative, so I know that that's possible. It's just not if it's an even. So I'm going to look for groups of 5. So I'm just going to go ahead, and I already know that an odd index with a negative number is going to be negative. So I'm just going to go ahead and start by saying my answer is going to be negative. All right, and then I'm going to go over here, do 32, 32 divided by 2, 16 divided by 2, 8 divided by 2, 4, 2, and 2. Okay, I have a group of 5 2's, so that's just -2. That just means that 32 is a perfect 5th root because I have nothing left over. Okay, here I have an even index with a negative number. Well, that's not going to work because there's no negative number I can multiply by itself 4 times to get to a negative number. So this is no solution. So you just saved yourself all that work of trying to find groups of 4 and 625. Okay, here I want groups of 6, and I have 7/64. Well, I can't simplify this fraction, so I'm just going to split it up. I'm going to say, all right, what's the 6th root of 7 and the 6th root of 64? Well, 6th root of 7, 7 is a prime number, so that's just going to have to stay 6th root of 7 on the top, which is okay to have a radical in the numerator. All right, I'm going to work on this 64 and see if I can get a group of 6 something. So I have 64 divided by 2, 32 divided by 2, 16 divided by 2, 8 divided by 2, 4 divided by 2. Okay, see how I have 6 2's out here? So I know that this is 2. However, when I was doing this, really we should have been able to stop at 32 because right up here we saw that 32 had 5 2's in it. So I already knew that I had to have 2 and I was going to get 5 more, so I had to know that this was going to work out this way. Okay, cube root of 81, x to the 4th. Well, 81, you should know by now. Let's see. 81 divisible by 3, 27. Divisible by 3, 9. Divisible by 3. Okay, so I have a group of 3 3's, right? Because I'm looking for groups of 3. So the 3 goes on the outside. And then, 3 goes on the outside. And can I take a group of 3 x's out of this x to the 4th? Yeah, I have 3 x's in there. So I can take one out, a group out. And then what I have left is this 3 on the bottom that was left over. And one of the x's in here. Because remember, I took 3 out. And I need to make sure I put my little 3 here, my index. All right, here I'm looking for groups of 4. Well, I shouldn't have to write out y 12 times. So you got to think, how many groups of 4 y's can I take out of 12 y's? Well, I can take 3 groups out. So this is just y to the 3rd. There's none left over, right? Okay, here I have a negative number, and I want to take an even root of that negative number. Well, that's not going to work. We already know that, so that's no solution. Okay, here I want groups of 5. And again, I shouldn't have to write out all these A's, all these B's. Just how many groups of 5 A's can I take out of 7? Well, I can take 1. And then how many groups of 5 B's can I take out of 2? I can take 2 of them. And what do I have left over? I still have these 2 A's that are left over from the 5 that I took out. So A squared, and I need to remember to put my little 5 there. Okay, here I want groups of 6. So how many groups of 6 x's can I take out of 12? 2 of them. How many groups of 6 n's can I take out of 18? 3. And if you don't feel like you get that, then you can just write it out. But that's going to take you a long time if they end up being big numbers. Okay, now think about this. This 4 is on this whole value of 18n. So this is like, inside of this, it's like 18n times 18n times 18n times 18n. Well, how many groups of 18n's can you take out of 4 18n's? You can take out 1 group, so it's just 18n. So remember, roots and whatever their index is, they're inverse operations. So these 4's just sort of cancel each other out. Okay, here I want groups of 5. So let's work on the coefficient first. So 243. 243 is not divisible by 2, but it is divisible by 3. So 243 divided by 3 is 81, which is divisible by 3, 27, divisible by 3, 9. Okay, I was looking for a group of 5. So I actually have 5 3s, so I know a 3 can come out on the outside. How many how many groups of 5 A's can I take out of 8? Well, I can take 1, and I'm going to have 3 left over inside, right? And then how many groups of 5 B's can I take out of 15? Oh, actually, I can take 3. So I have 3ab cubed, 5th root of a cubed. Actually, I'm going to write it a little bit neater because sometimes the exponent up here gets a little mixed up with the index that's right next to it. So you want to make sure that those two numbers are separate. Okay, last one. Let's see, I have a negative number under here and an odd index, 3. Okay, I know that that's possible. And not only do I know it's possible, I know that I'm going to end up with a negative answer. So you should know by now, 125 is a perfect cube. So I know that I can take, it's 5 times 5 times 5, so I can take a group of 5's out. And how many groups of 3 x's can I take out of 6? Oh, I can take 2 of them out. How many groups of 3 y's can I take out of 8? Well, I can take 2 groups, but I'm going to still have 2 left over in here. So y squared, right? Because this is like, I can split it up into y to the 6th, divided by 3. I have 2, and then I have 2 left over. But I don't want to forget this little 3 as my index. Okay, I know we went through the last page kind of fast, but at least you have it and you can, pause and go back. But I hope that helps you with lesson 6.2e, and I hope that it'll help you with completing your homework. All right, have a good day.